Okay, just a little while ago, I sent you a practice free response kinetics question from an old AP exam on Remind. This video, I'm just going to make a little short video to walk you through the scoring guide for that. And now that you've had a chance to try it for yourself and see how you did. This is a short 4-point free response question from the 2014 AP Chemistry exam. Okay, so the reaction discusses, the question discusses the isomerization of cis-butene to trans-butene. Butene, you'll remember butene is, but means 4-carbon chain. Ene tells us that it has a double bond. And the cis versus trans, cis is when your functional groups are on the same side of the double bond. And trans is when those groups are on opposite sides of the double bond. So this is not exactly a reaction, it is an isomerization. And you'll remember isomer is one of our vocabulary words. An isomer is a compound that has the same formula, but different reactivity and different function. Okay, so we are given a data table that has 4 trials with each one has initial pressures of cis-butene. So they give us the pressure in torr for the starting material. And then we also have the volume, the temperature that the experiment was done, and the half-life for that isomerization. So trial 1, half-life, trial 2, trial 3, trial 4 is different because it's done at a different temperature, different half-life. The questions, 4 parts, okay? So I'm going to switch my view to my notebook and then we can walk through working this out together. Okay, let's get that where you can see it. All right, so I've kind of copied the problem for us here. Okay, so the first part of the question asks us to explain how we can tell from the data table that this is a first order reaction. So I hope that you wrote that in a first order reaction, what did you write? So a first order reaction always has a constant half-life at a given temperature. And so we can use experiments 1, 2, and 3 to justify that this is a first order reaction because when the temperature is held constant at 350 Kelvin, the half-life is also constant. So first order reactions have a constant half-life at a given temperature or at a constant temperature. So trials 1 through 3 show this to be true. Demonstrate this, and this is a 1-point question. You had to use trials 1, 2, and 3 and reference the fact that half-life is constant for a given temperature. If you did that, give yourself a +1. Good job. All right, so let's look at the second piece of that. Calculate the rate constant at 350 Kelvin. So, rate constant, how am I going to get that? What do you know about the rate constant? Well, you probably remember that K is equal to 0.693 divided by the half-life for first order reactions. And if you don't remember that, then shame on you, but also it's on your helpful information sheet. So anytime you're working your free response questions, anytime you get to a sticking point, look back at that helpful information sheet, see what information is available for you there. This is in the kinetics box on the free response sheet, and it only applies to first order reactions. And so we are asked to calculate the rate constant at 350 Kelvin. So let's do it. But we have to remember for rate constant, you need to make sure that you get your units correct. And this one is not hard, but you got to put it in there. So 0.693 divided by my half-life at 350 Kelvin is 100 seconds. So divided by 100 seconds, and that's going to give me, move your decimal over twice, seconds to the minus 1. So 0.00693 seconds to the minus 1. If that's what you got, give yourself 1 point. For part C asks, is the initial rate of trial 1 greater than, less than, or equal to the initial rate of trial 2, and justify? So what do I know about trial 1 and trial 2? Let's see, they're both done at 350 Kelvin. What is this? Is that a 2 or a 4? That's a 2. So the volume is the same on both, the temperature is the same, the half-life is the same. The only thing that changes is the pressure. We don't know, you do know that if the concentration is higher, the initial rate is higher, but the same is true for pressures. Remember, rate equals K times the concentration of your reactants. So K times, I don't know the concentration, but rates, here are my reactants, my cis-butene. Okay. Rate is also equal to K times the pressure of your reactants. And so just like with concentration or molarity, remember if it's in brackets, it's talking about molarity. They're used in units of moles per liter. Pressure can be a stand-in for molarity. They do not have the same units, right? Our pressure here is in torr. Molarity is moles per liter. Totally different units, but the effect is the same. So the rate is also, for gaseous reactants, our rate's going to be higher when the pressure is higher. And so comparing trial 1 and trial 2, it asks is trial 1 faster or slower? What does it say? Is the initial rate of trial 1 greater than, less than, or equal to? So we should say something along the lines of trial 1 has a, trial 1's initial rate has an initial rate that is lower than trial 2. Less than trial 2. Because the initial pressure is lower for trial 1. Okay, so to get that point, to get the 1 point for part C, you needed to reference the initial pressures and say that trial 1 would have a lower initial rate than trial 2 because the pressure is lower. You could have used the given data and calculated the concentration, but it's not necessary. But that's another way that you could have gotten that point as well. All right, so the last point, point D, says explain why trial 4 has a lower half-life. Well, did you notice that? Half-life is 100 seconds when we're at 350 Kelvin. The half-life drops to half of that, 50 seconds, at a higher temperature. Why is that true? So part D asks us to explain that in terms of the activation energy. When they tell you in terms of the activation energy, you better use their cue there, right? Use that as a clue to guide you on how to think about this. So we're going to explain this in terms of the activation energy. So what is true for trial 4? It's done at a higher temperature. If the temperature is higher, what do you know about the molecules? You know that, what's going to be true about them? In trial 4, the molecules have a higher temperature. Come on, I know you said it. And so they have a higher kinetic energy. Higher kinetic energy. And if they have a higher kinetic energy, then what do you know about the collisions? And thus, more successful. collisions that can overcome the activation energy. When you raise the temperature, remember the height of our hill on our energy diagrams is really our activation energy. If this is our energy of activation, when we raise the temperature, we're not shortening the height of the hill like we do with a catalyst, but what we're doing is raising the energy of our reactants. So our reactants go into our products. If we start this trial 4 at a higher temperature, we're giving those reactants higher initial energy, and so it's easier for them to overcome that activation energy barrier. And so because more of those molecules can overcome that activation energy barrier, we have the rate is faster, or the rate is higher, and so the half-life is shorter. It means we're using up our reactants at a much faster rate. So +1 for number 4, as long as you said something about the kinetic energy of the reactants being greater, and so you'd have a higher percentage of them that could overcome the activation energy for that reaction, for that process. Hope you got all 4 points and that you're enjoying your day. I'll talk to you soon. Bye.